Good morning, everyone. We will get started shortly as the room is filled with attendees. If you're just now joining us, good morning. We will begin shortly as we are still awaiting for participants to join this webinar. Please use the Zoom chat to let us know which county you're joining us from so we can get a better sense of our audience for this morning's webinar. The chat is open. Broward County, South Florida is in the building. Citrus County, Martin County, Collier, Miami-Dade, Orange County here. We have great representation throughout the state so far. Shout out to Marion County, Sarasota County as well. So good morning, everyone. We will begin shortly as the room is filled with attendees. So if you haven't already had the chance to do so, please use the Zoom chat to let us know which county you're joining us from so we can get a better sense of our audience this morning. Palm Beach, 561, Hillsborough County. Do we have anyone from the Panhandle here? Bay County, Escambia County. Okay, Leon County is here. Tallahassee. Polk County is here. I see some familiar names in the chat as well. Some of our FFL agents, FFL training agents, very familiar names. So good morning again, everyone. If you're just not joining us, welcome to the webinar. We are asking everyone to please input in the chat, in the Zoom chat option below which county you're joining us from, so we can have a better understanding of our audiences this morning. It is now 10:01. We will give participants maybe another minute or two to join before we begin this webinar. Escambia County, okay. I see representation in the Panhandle. Volusia County is also here. Broward County, Marion County. Very well. Another Escambia, Okaloosa County. Okay, we have the Panhandle here. So we have representation in the chat box from South Florida all the way up to Escambia County, Bay County regions in the Panhandle. So that is great representation. And as of right now, we have well over 100 participants. So thank you all so much for joining us. We will begin now, actually. Good morning and welcome to the Florida Friendly Landscaping Professional Webinar Series. My name is Mark Celestin, and I am the training coordinator for the Florida Friendly Landscaping Program, and we are excited to host you this morning. Your microphones have been muted. We will be closing the chat feature during the presentation. Please put your questions into the Q&A box once the chat option is closed, and we will take them at the end of the presentation, your questions. This webinar is approved for one, FFLCP, LIAF, FDAX, DBPR, FNGLA, and one ISA CEU. There is a $15 administration fee to receive a certificate for continuing education or CEU. We will put a link in the chat box to make payments for the certificate if you have not already done so. Let me go ahead and put that there now. You'll also see a survey invitation pop up. Please take a moment to complete it. It's an important tool that helps us shape future educational programs and better serve upcoming audiences. We will submit for CEUs to the licensing agencies on Friday this week. So please make sure to finalize your CEU payments by the end of the day today if you would like CEU credits for your attendance. Again, today's webinar is part of our monthly webinar series that is held on the second Tuesday of every month at 10 a.m. Eastern Time. Our next regularly scheduled webinar will be August 12th with Mark Frank, who will present on the topic Wildflowers and Weeds Exploring Nativeness. Today, we are thrilled to have you join us for our professional webinar entitled Microclimates Mitigating the Heat in Florida Cities, presented by our very own Dr. Yi Luau, professor in the Department of Landscape Architecture. Dr. Luau, PLA, ASLA, is an assistant professor in the Department of Landscape Architecture at the University of Florida. She holds a bachelor's of architecture, a master of landscape architecture, and a PhD in urban and regional science. Dr. Luau's research is centered on improving the intersection of landscape design, sustainability, and human health. Her expertise includes landscape performance evaluation, therapeutic landscape, microclimate heat, and stormwater management for low-impact development. Dr. Luau's research has been funded by various agencies, including the U.S. Department of Agriculture, the Landscape Architecture Foundation, and Jesse Ball DuPont Fund. Before pursuing her PhD, Dr. Luau practiced landscape architecture in the U.S., where she promoted green building and sustainable development in multidisciplinary firms. She is also a licensed landscape architect in the U.S. Since 2016, Dr. Luau has been contributing to the profession as the secretary and treasurer of the Sigma Lambda Alpha Landscape Architecture Honor Society. Without further ado, I present to you Dr. Yi Luau. Thank you so much.
Thank you, Mark, for the introduction. Good morning, everyone. Thank you for the opportunity to presenting here my research about microclimate. Can you see my screen okay?
Yes, everything is clear on our end.
Okay. Yeah, so like my main research area is evaluating built landscape projects and using this information to guide landscape practice. And one of the sub area of my research is on mitigating heat for outdoor thermal comfort. So today my presentation topic is microclimates, mitigating the heat in Florida cities. Here's an overview of today's presentation. First, I'll briefly introduce the characteristics of Florida's climate. And next, I'll cover some basic microclimate concepts. And then I'll present 3 case studies showing how landscape solutions can mitigate heat. And finally, I'll summarize the strategies most applicable to Florida for improving thermal comfort. So let's get started. First, let's look at some facts. Florida is the hottest U.S. state and is warming faster than global average. Its mean temperature has risen by 3.5 degrees compared to worldwide increase of 2.7 degrees. Records show that the summer of 2024 was the hottest on record in Orlando, Tampa, Fort Lauderdale, and Punta Gorda. Today, Florida experienced 25 heat days, which is defined as days with air temperature above 103 degrees. And by 2050, the number is projected to jump to 130 days, about 6 times the current total. So these longer, more intense heat waves carry serious health risks. Florida leads the nations in heat-related illness, such as heat stroke, organ failure, confusion, and loss of consciousness. And Heat now claims more lives here each year than hurricane, lightning, tornado, earthquakes, and floods combined. And in particular, outdoor workers are vulnerable, and they are up to 35 times more likely to die from heat exposure because they work outside for a long time every day. So this map illustrates the United States' primary climate zones. Florida falls within tropical and subtropical regions. Florida spans latitude 24 to 31 degrees north, a distance of over 400 miles. Its peninsula is surrounded by water, with the Atlantic Ocean to the east and the Gulf of Mexico to the west. And the Britton Hill, marked by the red triangle in the Panhandle, is Florida's highest point at 345 feet above the sea level. And it is also the lowest state high point in the US. The prevailing winds between the equator and 30-degree north blow from the east across most of the states. Florida spans 4 climate zones. Most of the state falls within the humid subtropical zone, characterized by hot, humid summers, mild winters, which is like the coldest months average range from about 27 to 64 degree, and evenly distributed rainfall with no true dry seasons. South Florida encompasses 3 tropic zones, including rainforest, monsoon, and savanna, all with mean monthly temperature above 64 degrees, and they differ by precipitation patterns. Tropical rainforest has no dry season, so every month receives at least 2.4 inches of rain. Tropical monsoon features a pronounced wet season and punctuated by a short dry spell. And tropical savanna has a marked winter by dry season. So among these, rainforest zone is the wettest and the savanna zone is the driest. However, all 3 are classified as wet climates. And next, I'll introduce some basic information about microclimate. And here are a few statements related to microclimates. I'll invite you to write your answers, determining whether they are true or false, and we will cover them in later presentation. So the first statement is that warm air is denser than cold air because it has more energy in it. Second, greenhouse gases are the major reason for global warming, so we should live without them. And 3, when the sun rises, it heats up the air. That is why we feel warmer in the sun. 4, a morning after night with a clear sky is warmer than a morning after night with a cloudy sky. And 5, the shade of a tree is the same as the shade of a building. Right? So please write down your answers. So why do we study microclimate? And because people love to spend time outside. However, in many cases, we only pay attention to physical elements such as benches, pavilion, trees, flowers in the built environment and ignore microclimate because it's invisible. Actually, thermal comfort microclimate is fundamentally important for well-loved outdoor spaces. Let's look at the big picture first. Earth received an average of 342 watts per square meter of energy as the format of solar radiation. Roughly half is reflected by clouds or absorbed by the atmosphere, and the remainder is absorbed by the Earth's surface. At the same time, the surface emits about 390 watts per square meters of infrared heat, more than incoming solar radiation. So without greenhouse gases trapping the energy, the planet would cool rapidly. Greenhouse gases reflect roughly 90% of the outgoing radiation back towards the surface, keeping us warm. So greenhouse gases are crucial. The recent discussion about impact of greenhouse gases is that there is a possibility of increasing greenhouse gas emissions due to the urban development causing global warming. but we cannot live without them. A microclimate is affected by a variety of factors, and today we will look at several that are closely related to landscape design. These factors include temperature, humidity, solar radiation, terrestrial radiation, and wind. And the first factor is air temperature. How does air get warmed? At the beginning of the presentation, we saw a statement suggesting that the sun heats the air, making us feel warm. However, this is not correct. In reality, most of the sun's solar radiation is absorbed by the Earth's surface. The Earth's molecule become energized and their temperature rises. Air molecules in contact with the ground then receive some of this energy. As the warm air rises, cool air moves into the space and get heated by the surface. So in short, air is mainly warmed by the ground, not directly by the sun. That means our choice of the pavement materials and colors play a key role in influence local air temperature. As air molecules move through atmosphere, they cool at a consistent rate. And when the air is dry, the temperature drops by 0.5 degrees for every 100 feet increase. And if the air is moist, the temperature drops 0.3 degrees for every 100 feet. And this has important design implications. In regions with significant elevation change, temperature at the base and summit of a mountain can differ considerably. And similarly, if we design a roof garden on the skyscraper, the temperature at the rooftop might be quite different from the ground level. Vegetation also affects air temperature by cooling the air through evapotranspiration. For instance, a moist lawn can be 10 degrees cooler than the bare soil and as much as 30 degrees cooler than the unshaded asphalt. In addition to air temperature, humidity also plays a significant role in people's thermal comfort. Humidity refers to the amount of water vapor in the air, and this capacity depends on air temperature. The warmer the air, the more water vapor it can hold. For example, at 86 degree, air can contain more than 3 times as much water vapor as it can at 50 degree. So in hot, humid conditions, the air is close to saturation, leaving little room for additional water vapor. As a result, perspiration cannot evaporate efficiently, making people feel oppressively hot during periods of high humidity. Humidity is influenced by several factors. Sites near large body of water, such as lakes or oceans, tend to be more humid than inland areas. And wind direction also plays a role. Areas downwind from water source experience high humidity than those upwind. Additionally, vegetation increase atmospheric moisture through the process of transpiration. There are two main approaches we can use in design to modify air humidity. When the air is hot and dry, adding water and allowing it to evaporate can increase humidity and cool the air. And the top image shows an example from India. It is an award-winning building project. The building is elevated above the ground with the pool of water on its first floor that cools the structure through evaporation. So during the peak of summer, the interior can remain up to 20 degrees cooler than the outdoor temperature. In contrast, when the air is hot and humid, condensing water from the air can help make conditions more comfortable. The bottom image illustrates this effect. A cold bottle chills the air around it, and as the air cools, its capacity of host water reduces. So the water condensed onto the bottle surface. Well, this principle is mostly applied with mechanical systems such as air conditioning. And the condensed water is clean and can be used for irrigation if it's possible. And it's important to note that both strategies are only effective in a relatively isolated environment. Another important factor influencing microclimate is solar radiation, which is the energy emitted by the sun. In landscape architecture, we often focus on intensity of the radiation, which is the amount of solar energy received per unit area, such as per square mile. The intensity of solar radiation depends on the angle at which sunlight strikes the surface. So in areas near the poles, the sun hits the lower in the sky, spreading its energy over a larger area and resulting in low intensity. And conversely, near the equator, sunlight is more direct, concentrating in the smaller amount of energy over a smaller area, and then leads to a higher intensity. This is why polar regions are much cooler than equator areas. One statement we reviewing at the beginning was that the shade of a tree is the same as shade of a building, and this is actually not correct. Even though in reality, sometimes we cannot tell the difference, but there is a difference. Tree canopies allow a significant amount of solar radiation to filter through the leaves, while buildings provide nearly complete blockage, so it's cooler under the building shade. Terrestrial radiation also plays an important role in microclimate and should be considered in landscape design. All surfaces on Earth with a temperature above absolute zero, which is negative 459.67 Fahrenheit degree, emit heat in the form of terrestrial radiation. So that means almost everything we see in the world emit terrestrial radiation. And this type of radiation is invisible to human eyes and often overlooked in design. The amount of radiation an object emits is related to its temperature. The higher the temperature, the more radiation it emits. And this equation determines how much radiation an object gives off. The sigma is a constant equal to 0.000, loss of 0.567. And the K is the object's temperature in kelvins. And the bottom is the equation that converts Fahrenheit to Kelvin. So for example, if a person's clothing temperature is about 72 degrees, it emits approximately 429 watts per square meter in terrestrial radiation. The temperature of a clear sky around midday is about negative 4 degrees Fahrenheit, resulting in the sky emitting roughly 200 watts per square meter of radiation. So in comparison, as we just calculated, a person emits over 400 watts per square meter. This means that when we are outside, we lose energy to the sky. However, we don't feel cold most of the time because during the day, this energy loss is offset by the incoming solar radiation. But at night, when there's no sunlight, the energy deficit becomes more significant. If there are clouds in the sky at night, they emit more terrestrial radiation than a clear sky, which helps balance the energy exchange. As a result, mornings are more warmer after a cloudy night compared to a clear night because the cloud cover acts like a blanket, reducing the heat loss from the ground overnight. And the implication of terrestrial radiation for landscape design is that when trees are present on a site, the tree top exchange terrestrial radiation with the sky, while the bottom of the tree canopy exchange radiation with the ground, and creating a balance. So as a result, on clear, cool nights, people tend to feel more comfortable under trees or overhead structure because they do not lose energy to the sky. Wind is the movement of air from regions of high pressure to regions of low pressure. Cooler air creates high pressure and warmer air creates low pressure, as shown in the diagram. And many factors can influence the wind, including landform, trees, structure. They can change the direction and the speed of the wind. The effective, in some occasions, not always in Florida, we use wind blocks to block the wind, reduce its speed, and the effectiveness of a windbreak is closely tied to its height. Wind speed is significantly reduced within a distance up to 3 times the height of the windbreak on the sheltered side. Convection refers to the transfer of heat by moving air, and two main factors influence the amount of convection: wind speed and the temperature difference between a person and the surrounding air. So faster winds increase heat transfer and a greater temperature difference between your body and the air, resulting in more rapid heat loss. And this is why we feel much cooler on windy winter days than on warmer summer days with only a gentle breeze. Um, Winds near body of water follow a distinct pattern due to the difference in temperature stability. Water temperature changes more slowly than land. So during the day, land heats up faster under the sun, creating lower air pressure over the land. So winds blow from the water towards the land. At night, land cools more quickly than water, resulting in high pressure over land. So winds shift and blow from land back towards the water. So this summarizes like the basic concept of microclimate, and I found some examples of designs in Florida that try to mitigate the heat. And common strategies include incorporating wide roof overhangs, adding verandas for sun and rain protection, and orienting house with their long axis east and west to minimize morning and evening sun exposure. And next, I'll share some case studies that demonstrate the effectiveness of these heat mitigation strategies. The first case study is St. Peter Pier. St. Peter Pier is a historic landmark in St. Petersburg, located in the heart of the Tampa Bay near downtown. Over a century ago, the pier served as a gateway for goods entering the city, and later it evolved into a recreational destination. In 1973, it was rebuilt and with the iconic inverted pyramid as its head, becoming a recognizable symbol from both land and water. In 2015, Ken Smith won the public competition to redesign the pier with his team responsible for the 12-acre pier park to the right of the red line on this map. And later, W Architecture and Kibbley Horn collaborated on the west side, designing the 14-acre pier approach. So in 2020, the transformed 26-acre waterfront park officially opened to the public. My research team was selected in 2023 to evaluate the performance of this pier, and microclimate is one aspect we evaluated. St. Petersburg is located in southwestern Florida, which can be extremely hot and uncomfortable in summer. However, this pier has become one of Florida's most popular summer destination. So we want to see whether people are able to enjoy it in summer. The design incorporates extended roof structures and buildings to provide ample shade. And in addition to that, they add 800 trees to help mitigate heat and create a more comfortable environment. This picture shows the pre-development condition. This slide shows the post-development condition. We can see there's a lot of more vegetations on site. We use an all-in-one weather station to monitor microclimate, as shown in the top image here, and also a thermometer gun to measure surface temperature. And we select multiple locations to measure. Some locations were exposed to direct sunlight, with others beneath the shade structure and trees. We collect the data at three different times: morning, afternoon, and evening, on a typical June day in 2023. And the map here shows the measurement locations. We initially selected 9 sites for morning measurements on June 9th, 2023. However, after noticing several additional areas where people gather in the afternoon, we expand our measurement to include 8 more locations. And here's a snapshot of some of the data we collected on site, including solar radiation, air temperature, wind speed, relative humidity, and solar elevation. We input these measurements into a model to estimate energy budget, which serve as an indicator of thermal comfort. The charts on the left display both surface and air temperatures, which follow similar patterns. However, surface temperature were significantly higher than air temperature. While air temperature range from 82 to 95 degree, and surface temperatures ranged from 80 to 167 degree. And the locations on the right side of the charts, uh, most of them were in shaded, so they are noticeably cooler than the locations on the left of the charts. These charts display wind speed and the relative humidity. Wind conditions on the site were generally calm, with little variations in speed. And relative humidity also remained fairly steady, consistently ranging from 50 to 60%. These charts display solar radiation and energy budget, which we use as an indicator for people's thermal comfort. The energy budget represents the net energy we gain from the surrounding area. The result reveals that solar radiation and energy budget follow nearly identical pattern, indicating that solar radiation is the primary contributor to heat. And to improve thermal comfort on site, designers should prioritize blocking solar radiation with trees and shade structures. And here is a zooming situation for one of the shade structure on site, which is called the tilted lawn. We can see that if a person standing in the sun, they can gain 196 watts per square meters of energy. However, if they stay underneath the tilted lawn in shade, they only got 50. And according to the criteria, 196 is very dangerous. People need to use the site with caution. However, if they stay under the tilted lawn in the shade, they only got 50, which is considered safe and comfortable throughout the day. And this result clearly demonstrates that shade structure are effective in improving thermal comfort for visitors. My second case study is Mallory Square in Key West, Florida. In the summer of 2023, I collaborated with Sasaki, which is an interdisciplinary design firm in Boston, on a project at Mallory Square in Key West, Florida. Mallory Square is an iconic destination at the top of nearly every visitor's to-do list. Each evening, crowds gather to watch the sunset and enjoy performance of local artists. However, outside of an hour and a half before sunset, very few people use the site, just despite the great view of the ocean, just because it's too hot. And to address this, the city hired Sasaki to redesign Mallory Square, aiming to transform it into a place where people feel comfortable gathering throughout the day, whether to grabbing lunch from the vendor or attend morning yoga class. And this slide presents a visual map of thermal comfort levels at Mallory Square, with red indicating the least comfortable areas. And we can see that that's just like most part of the site. So this map is based on like the data we found online. The actual microclimate condition can be different on site. So to gain a more comprehensive understanding of the actual comfort level and to establish a baseline condition for further performance evaluation, we conduct the on-site microclimate evaluation. So here is the main team members on this project, myself and Alison Manthoff, who is the director of the strategy initiatives at Sasaki, Dr. Robert Brown from Texas A&M University, who is a renowned expert in microclimate research, and Karen Williams from the city of Key West. And here is our project plan. First we collected baseline microclimate data using thermometers and weather station on selected hot summer days. And next, we use modeling to calculate the energy budget, giving us insights into people's thermal comfort. And we then created and analyzed the various design scenarios to assess how specific design interventions can improve comfort levels. And based on these findings, Sasaki will develop final design solutions. And we plan to have this project constructed and then reevaluate microclimate condition on the site to see whether the applied strategies can make people feel more thermally comfort. So this slide shows the site map and our measuring locations. We include points both within the Mallory Square and in nearby offsite areas for comparison. Measurements were taken on 2 days in July, capturing 4 time periods, morning, noon, afternoon, and evening. And these photos, arranged chronologically, show that the site remained relatively empty during the day. This table provides a snapshot of the data we collected at each measurement location. For each site, we recorded solar radiation, wind speed, air temperature, just very similar to St. Peter Pier. And then we put this into the compound model as well. This slide shows illustrate how several parameters change throughout the day. So each of them is one parameter, and then the x-axis of these charts shows the time periods, morning, noon, afternoon, and evening, and y-axis shows different parameters. The different color lines represent different measuring locations. So for solar radiation, it peaked at noon and in the afternoon, but among the 7 locations, location number 5, which is a shade with shaded trees and which is shaded by trees and also 2 buildings, had the lowest solar radiation levels. And in contrast, air temperature remains relatively steady throughout the day, ranging from 86 to 96 degrees, which resulted in a consistent warm atmosphere even during the early morning and nighttime. Relative humidity also showed little variation over the day, staying between 57% to 75%. And location number 5 has the highest relative humidity, likely because it has lots of vegetation around it. And this slide explains, as we said, we put the data we collected on site into the compound model, and then we estimate the energy budget. And this slide explains what the energy budget means for adult heat health. And the gray area indicate that caution is needed for using the site. Pink represent extreme caution, and the area values above that means classified as dangerous, and the red area is extremely dangerous. We can see that like majority of our measurement is either in dangerous or extreme caution, highlighting that just during the day, it's really uncomfortable. And next, we try different design strategies to see whether they can help mitigate the heat and make people feel more comfortable. And we try planting trees, add shade structures, use different pavement, or add wind, like fans to the site. And here's the result. So we did this for every location we measured, and I'm showing the location number 2, which is the water edge and the most popular spot. So we found that if we plant trees to the site, they can reduce the energy budget by 44% to 59%, depending on tree species and the time of the day. If we installing shade structures like pavilions or canvas, they can provide even greater relief, lowering the energy budget by 52 to 67%. We also try to changing the pavement materials, and we have a mixed result. Among the more than 15 options of pavement, moist gray pavement was the most effective in lowering the energy budget. But during the evening, it actually increased the heat because the terrestrial radiation. So that explains why there's a negative value here. And similarly, increased wind at the site offered little improvements in thermal comfort due to the high humidity. So if we combine all these strategies, we can reduce the energy budget at location number 2 by up to 68%. This chart provides a quick comparison of energy budget between the existing condition and those with the design intervention. So the red line represents the existing condition and the orange line represents the condition with the intervention that we just mentioned. And we can see that with those interventions, the number 2 throughout the day is in the gray area, which is much better than the existing condition. So we have present this result to Sasaki, and we hope that this can contribute to a more comfortable and enjoyable environment for future visitors to Mallory Square. My last case study is Flip My Florida Yard. Flip My Florida Yard is a TV program focusing on transforming home landscapes into environmentally friendly yard. With experts from a variety of fields, the team transformed people's yards in just 8 hours. This quick turnaround time offers a unique opportunity to measure ecosystem services before and after the flip. So our goal was to identify ecosystem services resulting from Florida-friendly landscapes and use appropriate metrics to compare the pre- and post-project conditions of these ecosystems. We met with the TV team and identified the following aspects to measure: microclimate, stormwater runoff, wildlife, operation and maintenance, and overall satisfaction. And for metrics requiring on-site measurement, we selected 3 properties from each season, resulting in 9 properties, which are shown on this map. And for operation, maintenance, satisfaction, we surveyed all 30 homeowners from their first 3 seasons. Next, I'm going to share the findings of microclimate and also the usage, which is influenced by microclimate. We visited the selected property in July 2024 and measured the microclimates. And for each property, we took 5 measurements. The first measurements were taken at a nearby street, not on the selected property. And this measurement is used as a control location. And after that, we measure 3 locations on site. And finally, we measure the first location again, considering that microclimate might change during our measuring period. So the 2 sets of data at the beginning and the end can help us interpolate the measurements. And here's a snapshot of the measurements we took on site. Similar to St. Peter Pier and Mallory Square, we used the weather station and the thermometer gun, and the data we collected are very similar: solar radiation, surface temperature, air temperature, wind speed, humidity, and etc. And we also recorded the ratio of building, vegetation, and sky at each measuring location. And then based on this data, we used the cone file model to developed by Dr. Robert Brown to estimate thermal comfort, which is shown in the last column of this snapshot. Due to the tight time frame, we didn't measure all 9 selected properties. We were only able to measure 7 of them. The top left diagram compares the on-site measurements with the weather station records, including relative humidity, air temperature, and wind speed. And it indicates that the on-site records were not that different from the weather station data, especially for air temperature and wind speed. And the top right diagram summarizes the comparison of thermal comfort between the control location on the street and the properties. So in this chart, pink indicates a preference to be cooler, and red indicates that people would prefer to be much cooler. So for most of the properties, the yard and the control point fell into the same category, except for properties 5 and 6, where the yards were cooler. And the bottom right chart shows the heat health result. In this chart, gray represents a need for caution. Light pink indicates a need for extreme caution, and pink means dangerous. And again, for most of the properties, for half of the properties, the control point and the yards were in the same group, except for properties 3, 5, and 6. And in hot summer conditions, solar radiation is the main source of energy. So the bottom left diagram shows the relationship between solar radiation and the energy budget at our 35 measuring locations. And we can see a similar pattern, except for larger range for solar radiation. Um, so knowing that like property 3, 5, and 6 have like the cooler environment compared to the streets control points, so we want to see their landscape design. And this pie chart shows the ratio of sky view and tree view factors. So blue represent sky and orange represent tree. And the pie chart shows their relevant ratio. We observe that the ratio of tree view factors for properties 3, 5, and 6 are larger compared to other sites, contributing to their cooler microclimate. So the bottom left chart illustrates the relationship between sky ratio and the energy budget. As the sky ratio decrease, the energy budget also decrease. And this means that by providing more overhead coverings, people will feel less hot. And it needs to be noted that the Flip My Florida yard was not completed very long ago, so the plants planted on site needs time to develop. I believe if we do this research again in a few years, the result will be much different. So we think this microclimate contribute to the usage change of the yards. So so here's the result for the usage of the site. We want to understand when homeowners use their yard. So we use a scale where 1 means least likely and 4 means most likely. And we ask for their usage in 4 time periods: morning, afternoon, evening, and night. So the most popular time to use the yards was in the evening, both before and after the flip. However, the morning saw the largest increase in usage with 79 rises. The smallest increase was in the afternoon at 41%, which was also substantial. So as for the time spent in the yard, we observed an increase from an average of 1.7 hours to 4.14 hours per week. So in conclusion, the sun provides the main source of heating for objects. It moves in a predictable way through the sky. Normally, it is easier to reduce the input of warmth than to increase it. The wind provides the main source of cooling for warm objects. It moves in the somewhat predictable way through landscape. It is easier to lessen the velocity than to increase it. Air temperature and humidity cannot be modified largely by the landscape, except in specific circumstances. In summer, the biggest impact a landscape can make is to reduce the solar radiation absorbed by an object. And when we do design, need to consider the energy balance and think of the heat added to a person, mostly due to solar radiation and terrestrial radiation from objects around it. And the heat carried away from a person, mostly due to wind and terrestrial radiation. This chart shows a summary of different strategies for different climate zones. And most of Florida are within hot, humid zone. So here are the strategies for sun, wind, and water. So for the sun, we can consider maximizing shade through planting trees and provide overhead structure. And we can also consider providing large overhangs and building using high ceilings and vent all roof system. For wind, we can consider siding structure at the top of the slope for exposure to breezes, avoid excessive thermal mounting that may trap moist air, and maximize breeze through the use of high canopy trees and with loose open planting patterns, and avoid tall solid walls that block wind. And for water, because it's humid, we need to consider infiltrate the stormwater runoff. Do not let the water stand on the site. Also avoid siting next to a stagnant body of water. And lastly, I'd like to highlight two of my students' outstanding projects. Rebecca was a Bachelor of Landscape Architecture student at UF. She graduated last May. Her capstone projects, Cooling the Sunshine State, present heat mitigation strategies for policymakers, designers, and homeowners. And Ray Hu is my PhD student, and a part of her dissertation explores how trail design influences outdoor thermal comfort for older adults. So if you are interested, I'd like to share more details about their work. Most of the knowledge about microclimate are based on these two sources. Thank you very much for your attention. Please let me know if you have any questions about any part of the presentation. Also, feel free to reach out later if you want to discuss this topic more. Thank you.
Thank you so much, Dr. Luau, for a wonderful presentation on highlighting your different case studies throughout the state.
Mhm.
Commendable. We do have a few questions here in the Q&A. Shouldn't take us too long. We have 10 more minutes scheduled on our original scheduled time. Our first question here reads, we have been told that Orange County is now zone tropical. Is this true?
I think it might be true. I didn't know exactly if Orange County is considered subtropical, but there has been discussion about like the changing of the climate zones with the global warming. The like tropical zone is expanding. So I think that's possible.
Thank you for that response. The next question is, are you using solar panels to create shade roofs in any of your installations?
Um, I think for the project I studied, um, I think St. Peter Pier, they do use solar panel on the parking roof. So they install that on top of the roof, and we also calculate how much energy they can generate. But I think um, yeah, I think it's just the one feature that create two benefits: generate energy at the same time for provide shade. Um, we didn't measure the area underneath the solar panel just because we only had one day visiting St. Peter Pier, so we select the area that people visit the most. But I think that's a good point that using a solar panel as a shade structure, and I do see many practice like that.
Thank you so much for that response. And then we have another question here from Donna that reads, even though trees and buildings can provide the same amount of mitigation, wouldn't trees also provide more benefits such as O2 and wildlife habitat and should not be considered equal?
Yeah, definitely. I think yeah, well, I think what presented like more like a simplified when we look at shade and like microclimate improvement, we only focused on that. But definitely, even though shade structure, like a building structure, they can provide more blockage of the solar radiation, they do not provide benefits like habitat for wildlife, like CO2 sequestration, or like food for animals. I think it provides more benefits and to people's mental health. So when we do design, we definitely need to consider multiple aspects, not just the focus on microclimate.
Thank you for that. Um, we have another question here. It's a very long one. It's multiple parts, so I can reread it for you if you would like. But it starts by saying, regarding materials and reducing energy budget, are there any insights regarding the ultra white paint developed by Purdue?
Mm, no, I think the compound model we rely on, they at this point they only include like most popular building materials, and I believe the 15 different pavement materials we used in the model, they do not include that one produced by Purdue. But I think, yeah, if this is new material, it will be interesting to see its performance to measure that and to incorporate that into that model and to see whether it's valuable for mitigating microclimate. Mhm. Yeah, thanks for
Thank
mentioning.
you. Thank you. Yeah, and you did go into the second part of the question as well. So we are moving on to the next question. One of the attendees noted that some of the photos on the classification slide may have been mislabeled. Would you be open to taking a moment to clarify or confirm the labeling
Which one is that?
on one of your earlier slides on classifications, different classifications?
This one?
I believe so. And I'm not sure which slide specifically, but this question just says the classification slide. Um,
For the climate zones or mm,
okay. Well, we because we're not sure which slide is being mentioned, can we just move on to the next question here? And Dr. Luau, maybe we can share your email address at the end if
yeah.
someone have a specific question relating to your presentation today. They can certainly get in contact with you via email. Is that correct?
Yes, yes. Here's my email. Feel free to contact me if you have any questions or want to discuss more.
Thank you. And now the last question we have here is, do you see palm trees being a factor in mitigating wind damage in a hurricane?
Mm, mitigating
Trees.
trees. Um, I do see palm trees as a contributor to like more comfortable microclimate because when we measure those home properties, we do see lots of palm trees used on like residential property, and they do make people feel comfortable. But like a wind block, I think it depends on how many of them. Like if you just have a few of them as wind block, I don't think they're that effective. But if you have rows of that, maybe that's a different story.
Thank you. Thank you so much for those wonderful responses, Dr. Luau, and thank you so much for a wonderful presentation for this month's professional webinar. Thank you again, everyone, for attending. Just a reminder, today's recording will be posted on our FFL website. We do ask participants to allow 1 or 2 weeks for us to package that recording accordingly before it is reflected on our website. Um, Dr. Luau did share her email address, but I'm going to paste it in the chat box again. If everyone would like to follow up, maybe have specific questions in reference to her specific case studies, so on and so forth. This would be the go-to email to utilize, yi.luau@ufl.edu. Thank you so much. If you don't have anything else, Dr. Luau, you are free to go. Thank you so much, everyone, again.
Thank you, everyone.